Okay, this paper comes from the MCQ book, the Marshall Cavendish MCQ book, chapter 14, periodic table. Okay, let's run through the questions. Okay, so level 1 question will be quite easy, but needs a bit of memory. So what's the use of a noble gas down here, which is not a use? So for example, light bulb you use argon. Argon is used in light bulb. Okay, and weather balloon you use helium. Inner atmosphere in the welding itself, you use argon. All these three are the examples of the uses of the noble gas. And to store alkali metals, they don't use gas. They use oil. Oil is alkali metals are stored in the oil. So answer is D. This is not the use for noble gas. Cannot. Not practical. Because metals, if you store in noble gas, you take out, you put in, you see that you use it very often, like alkali metal you do for experiment. You take out one piece, you cut it out, you put it back. So you cannot be keeping in the noble gas environment for long. Unless you got a container that's noble gas, in a cylinder, then you got to refill the noble gas inside there. It's not practical. Yeah, not practical. And alkali metal react with air very fast. Before you fill up with noble gas, you expose the atmosphere, you get oxidized already. So oil is actually one of the more practical way to store it. Not that it cannot, but it's not a practical way. All right, unless you have to store a piece of metal for exhibit for a very long time. Yes, maybe you have to cut the metal in the noble gas environment. For example, you have this particular fume cupboard kind of thing where inside is filled with noble gas. Of course, you cannot be inside because you cannot breathe, right? So noble gas, so you actually take the metal, put inside this cupboard, inside filled with noble gas, you cut it, you remove the outside layer, then you put back in the container, then fill the container with noble gas. That is possible, not practical though. All right. So ABCs are the practical use of the noble gas, but not D. Okay, which of flowing is correct according to store alkali metal? So to store alkali metal again, you see the hint here is put inside oil. Okay, this is a typical way to store alkali metal because you want to keep it away from water and oxygen in the air. Which of flowing is not true of group 17 elements? Group 17 is the halogen, which is not true. Yeah, boiling point going down is increase down definitely. And because group 17 are simple covalent molecules, diatomic simple covalent molecules. As you go down, the molecular size increase, intermolecular force increase. Therefore, melting boiling point also increase because you need more energy to overcome. And group 17's most reactive non-metals, yes, because they only need to receive one electron and therefore they can react rapidly compared to other non-metals. They're more reactive. Reactivity increase down the group is wrong. Reactivity decreases down the group. So remember that in group 1, reactivity increases down because as you go down the group, easier to lose electron. That's why increase down. But group 17 is receive electron. As you go down the group, the ability to receive electron become lesser and lesser, weaker and weaker. So therefore, reactivity decreases down. And the form copper compound formula, this is not totally true because copper, okay, this is true. Okay, this is true. Okay, this is partly true. If they say this one is also possible true because, let me see, copper has copper 1 and copper 2. So copper 1 is CuX, copper 2 is CuX2. So generally, there's copper 2 will be CuX2, and this is true. Okay? If they say only form compound of this, then it's not true because can form both kind of compound. Copper 1 and copper 2 compound. Okay, number 4. Which of the following is true across period 2? True across period 2. So period 2, true. Okay, the size of atom decreases across. Atomic size decrease. Because as you go across period 2, there are 2 shells. 2 shells means maximum is, if the shells are in the equal spacing, then of course is equal size. But as you go across the period, the proton number increase. Proton number increase. So the nuclear charge increase. Okay, the nuclear EAR charge increase. So the nuclear charge increase means that the attractive force on the outer electron increases across the period. So when the nuclear charge increase, attractive force increase, therefore stronger attraction causes the outer electron to be closer to the nuclear. So in other words, the size generally decrease across the period. And that's true. Okay, which metal, number 5, which metal have the best electrical conductivity? Now down here is what are we looking at? Yeah, people who don't study physics probably don't really know this very well because electrical conduction has to do with the electrons that's moving. So down here, we're actually looking for the highest charge, no, let me see, conductor. Oh, no, sorry. This one, higher charge is aluminum, but best electrical conductor down here, usually they are transition metals. Transition metals can also lose the inner electron. Okay, so in this case, I think this is not a very common question. Copper, silver are very good electrical conductor, copper and silver. So down here, answer is copper. Silver is better than copper. Yeah. So other than, I think the whole idea is about transition metal being good conductor of electricity. Yeah, this idea. Aluminium could be also another possibility. After copper could be aluminium. Yeah. Aluminium has 3 electrons given out. So there's a possibility that aluminium is also a very good conductor also. Okay, next one, number 6. Okay, element X is found. The properties, brittle, dark solid, looks like it's a non-metal. It react magnesium form compound, looks like it's group 17. Okay, imagine putting chlorine into X position. Then you have magnesium chloride. Looks like okay, it's possible. When added silver nitrate, a brown PPT form. In other words, this is a brown PPT. Looks like silver, silver chloride, silver iodide kind of thing. So it's likely that the answer is this one. Now, how do you know it's 17? Is because of the formula. Mg2 plus X minus. Okay, so we know that it should be in group 17. If the formula is Mgx, then it should be in group 16. Definitely not in 18 because 18 don't form compound like this. 15, of course, is 3 minus. So answer is C. Okay, which of following is the reason why group 1 metals form alkalis instead of oxides when they're added to water? Okay. Okay. All metals will form oxide, but group 1 oxides are very soluble in water. Even they form oxides, they'll dissolve in water to form the hydroxide. And the hydroxide is called alkali. All right, so even if I have, let's say, group 1 metals, sodium form oxide in the air, and sodium oxide, the whole thing, sodium and sodium oxide together, put inside the water, even the sodium oxide also react water to form hydroxide. So key idea is they're all soluble in water. So they form alkalis. Alkalis are soluble base. Answer is A. Sorry? B? No. Group 1 also can form oxide and hydroxide both. Sorry, in the air. In the air. You will form metal oxide in the air. Yeah. Group 1 will not form oxide. Okay, even if you form oxide, you will form hydroxide straight away. Anyway, they will not form. I don't think they form oxide in the water itself. Down here it says only form. It doesn't say where is it. So group 1 can form both hydroxide and oxide. Yeah, why they form the alkali? Because they dissolve. Alkali is soluble. Okay, maybe down here they should write instead of forming, let's say, maybe the question is not very well expressed. Not only form oxide, it could be also form hydroxide. I think they're trying to say that why don't they form like insoluble metal oxide hydroxide? Because when it's oxide, when it's soluble, it forms alkali. So the alkali always remind us that the substance is soluble. Definition alkali is a soluble base, and it dissolves in water to form hydroxide ions. So keyword is soluble. Okay. Okay. No, the question quite difficult here. A lot of like reasoning. Which of following is not true about chlorine gas when bubble with potassium iodide? Not true. The truth is that they will undergo displacement reaction. Not true. Let me see. Let me see. Okay, displacement reaction, you will turn aqueous iodine will form. Aqueous iodine definitely is brown in color. So solution turn from colorless to brown. Okay, so down here is that the chlorine will actually displace iodine. Also means that you see the chlorine gas Cl2 plus Ki form KCl plus I2 to 2. Okay, so what happens is if I write in the ion equation, I become 2I minus 2Cl minus. So what happened is this one is oxidized and this one is reduced. Okay, so the chlorine will gain electron and get reduced. The iodide will lose electron and get oxidized. So in this case, iodine is the reducing agent, which is true because it's oxidized ma. So it's reducing agent. It reduces chlorine to chloride. So B is correct. And this equation, oh yeah, the same way I didn't realize it. This is the only equation that's correct. Okay. Chlorine is more reactive than this one and displaces iodine from potassium iodide. Now this is the statement. This is the true statement, explanation of that. So I'm going to remove this one first. I didn't realize this. Okay, this one is reduced. And this is oxidized. So if you're oxidized, you must be reducing agent. Let me just put on here, you must be reducing agent. If you're reduced, it must be the oxidizing agent. All right, so this is true. Color turns to brown. This is brown. This is brown. Okay, aqueous iodine is brown. Bromine is red brown. So remember that. Okay, can we move on? Okay, group 16 elements have similar group trends as that of halogens. In other words, going down the group, the reactivity will decrease, right? So combination of group 1 and 16, which one will produce the most vigorous reaction? Okay, you always look for group 1, the lowest, the group 16 or 17, the highest, opposite. So that will be the most vigorous. So if you look at periodic table, no, similar in the sense that reactivity. Trend, similar trend, not reaction. Trend means that as you go down, the group reactivity decrease. So the most reactive is on top, right? Fluorine is most reactive. So having the same trend means this is the most reactive. We're talking about reactivity in this case. Yes, melting boiling point also increase because any simple covalent molecules, as you go down the group, the molecular size increase. Molecular size increase means that the intermolecular force increase. Intermolecular force increase requires more energy to overcome. So for both, as you go down, the melting boiling point increases. But of course, the reaction of group 16, 17 are different now. Okay, but they all can react with metals. So answer should be the highest, which is oxygen here, and this one lower one should be rubidium compared to the rest. So answer is A. Yeah. Okay. All right, next one, number 10. Copper is used in electrical wire because it's a very good conductor. Even though copper should form this cation, conductivity is greater than most metal in group 2. Okay. Why does it that copper has greater conductivity? Okay, even though it form 2 plus, similar to group 2, why does it have better conductivity? Now, remember I mentioned the conductivity has to do with the electron movement electrons. So transition metal can lose inner shell electron. The details don't need to know, but you know that oxidation state of transition metal doesn't mean it's just uh, two. I mean, like doesn't mean just plus two. Remember, iron can be plus three or plus two, iron three or iron two. So iron is actually losing inner shell electron. Okay, same for other transition metals, they can lose from the inner shell. So therefore, the whole idea is that transition metal can lose electron from the inner shell. And therefore, they can lose, delocalize more electron, okay, have more delocalized electron than the group 2, because group 2 is limited to only the 2 electron in the outer shell. But copper can lose the 2 outer shell as well as inner shell. So therefore, they can lose more electron. Any transition metal can do that actually. All right. So that's why things like silver and zinc, we don't call them really transition metal because zinc always lose 2 electron only. You do have zinc 1, zinc 3, but just zinc 2. And silver is only silver 1. Okay, silver is a metal, but not really transition because it doesn't lose more than 1 electron. Unlike gold can lose 1 electron, can lose 3 electron. So we have commonly seen gold 1 and gold 3 ion and so on. So it's a transition metal. So characteristic of transition is that they can lose electron from the inner shell too. So they can lose more than just the outer shell electron, which is 2. Okay. Okay, let's move on to the next one. Okay, so reactivity. So, okay, if you can displace the other one means you're more reactive. So I will do working. For the first one, I'll put X above Y because Y is being displaced by X. And then the second one is X displays Z. So which equation which other equation do I need in order to show that the Z is the least reactive and X most reactive? I need to compare Z and Y. All right, I need to compare Z and Y, because if you put this together, two together, you realize that, hey, my Z and Y, I don't know who is higher than who. So I need to compare these two, and you know that Y is more reactive than Z, so Y must displace Z. Let's look for an equation that Y displace Z. Y displace Z, answer is B. Y method displace Z, Z comes out. So this reaction will show that my Y is more reactive than Z, and hence together Y more reactive than Z. So together with the other two equations, you know X is the most reactive, and then after that you know that Y and Z, Y is more reactive than Z. So you got this equation. Okay. If they say that Z is more reactive than Y, if the question say that Z more reactive than Y, then of course answer is D, because Z displaces Y. Okay, but now it's B. Okay, electron affinity is a tendency of an element to attract electrons into his valence shell to form an anion. It depends on the following: attractive force of the nucleus and as well distance of the shell from nucleus. Now, so this one we don't really study in detail, but this is the definition. In other words, the attractive force of the nucleus, the larger the nuclear charge, the more likely you could attract the electron into its valence shell, as well as the distance of valence shell from the nucleus. So do you remember like fluorine, chlorine, bromine? So fluorine has only 2 shell, 2, 7. This is 3 shell, 2, 8, 7. So comparing the distance from the nucleus, you realize that chlorine is further. Valence shell is further from the nucleus. Nucleus is inside here, right? Nucleus is probably somewhere here. Okay, the shell is 287, nucleus 27. So fluorine, the outer shell is closer, the valence shell is closer to the nucleus. Therefore, shorter the distance, the greater the electron affinity. So fluorine can attract electron more easily. That's why more reactive compared to chlorine. And of course, attractive force wise, if you look across the period, if you look at 2, 5, 2, 6, 2, 7, obviously the nuclear charge is largest for here because there are 9 proton. This is 8 proton. This is 7 proton. All right. So a 9 proton will definitely attract the electron into its valence shell more easily than the 8 proton than the 7 proton. So compare across a period for the fluorine, period 2, you realize that this one is the most reactive one. Strongest, highest electron affinity. Okay? As you go down the group, the highest one will be the highest affinity. So you realize that that's the reason why the right hand upper corner is the most reactive non-metal, because the highest electron affinity. So across a period, the electron affinity actually increases because the number of proton increase, nuclear charge increase, attractive force increase. Okay, due to nuclear charge. All right, down here, nuclear EAR charge increase. Okay, nuclear charge increase because proton increase. Yeah. Then down the group wise, you see that the shell become larger and larger. Larger shell means the distance is further, right? So as you go down the group, it decreases. Okay, because larger shell, valence shell further away, so the attractive force decreases. So answer is C. So this is a very good question. It actually explains why fluorine is the most reactive non-metal. Because across a period, fluorine is the most reactive across period 2 because it has the highest nuclear charge. So attractive force for electron into its valence shell is highest. But if we look down the column of group 17, it has the smallest atomic size. So the valence electron is nearest to the nucleus. So even though chlorine has more nuclear charge, but the electron shell is much further. All right, because the shells are actually very, very far away from each other. As you go further out, you go further and further. It's not proportional. It's not that the distance between a nucleus to the first shell, first to second to third is equal. It's not equal one. As you go out, it further and further it goes. So therefore, these 3 shells already mean that it's very far from the compared to the fluorine. So therefore, attraction force decreases quite a lot. Yeah. Okay, so answer is C. Okay, this is a good question actually. All right. Okay, I still remember one thing. How about we're talking about the ability to lose electron? Okay, how easily the electron form ions. If you realize group 1 as you go down, the other way happen, right? The distance become further. So group 1 as you go down, for example, if it's 2, 1, 2, 8, 1, 2, 8, 8, 1, and so on, as you go down, further away from nucleus, attractive force decreases, therefore you can lose easily. So group 1 is that if you go down, the nuclear charge is higher, but the distance is so far away that the attractive force become weakened, and the electron can lose very easily. That's why more reactive as you go down group 1. Then if you compare group 1 and group 2, again you compare group 1, 281 versus group 2, 282. Losing 1 electron is easier than losing 2 electron. Okay, if you compare across a period, group 1 and group 2, losing 1 electron is easier than losing 2 electron. So therefore, it's easier to react for group 1, more reactive in group 1 across a period. Yeah, so that's the opposite explanation of the reactivity of group 17 and group 1. Okay, next one, number 13. This has to do with transition metal. Okay. Not typical. Not typical. Let me see what the information they say. Okay, here. Let's highlight some key phrases. It's group 3. Group 3 actually is transition metal. 3 to 11 is transition. It form white oxide. Now, oxide is, do you realize the transition metal forms color compound? So white color is more for group 1, group 2, but interestingly, this one is white. Color solution, again, transition metal usually have a color solution. Like copper is blue, iron 2 is green. Okay, a lot of different colors for transition metals. All right, so colorless is also not very typical, but could be possible, yeah. Heating does not produce other compound. Let me see. When this one react with chlorine gas, okay, again, white chloride, very interesting, white chloride. Again, colorless solution. Now, you have been emphasizing the color down here. So color, we know that transition metal is color compound. So down here, let me look for color. Answer should be C. Okay, not typical, not typical, but doesn't mean that it's not transition metal. All right, because if we can form 2 oxidation state, then it is transition already. If you can form 2 oxidation state, yeah. But down here only show me 1. Anyway, not part of the answer lah. Yeah, because if they say that it only has, if let's say we conclude that scandium has only 1 oxidation state, like 3+, 1 oxidation state, then that is also not typical of a transition metal. But down here, that's not an option. All right. Now, can we say B? Scandium chloride is soluble in water. Think carefully. Most chloride are soluble in water. All right. So nothing to do with the transition or not. Even copper 2 chloride is soluble in water. Yeah. Burns in air. Most metal burns in air. Yeah. Correct. React with acid. Most of the oxides are basic oxide. They either basic or amphiteric oxide. So they all can react acids. All metal oxides can react acids. Okay, next one. Oh, this is interesting. The trend. Okay, so look at the trend across the period 3. Let's see what are the obvious one. Number of electron involved in bonding, of course, is wrong. Sodium has 1, give out 1 electron. Magnesium give out 2, aluminum give out 3, silicon share 4. But you realize as you go the other way around, it should go backward down. Okay, and then of course argon don't have. You cannot draw the argon because argon don't even involve any. Yeah, so it's like that. So probably the continue is like that. No, anyway, I don't think there's a one more line because argon don't even react. So it's like that until chlorine. Chlorine should be 1. All right, so not this one. Size of ion. Size of ion. Okay, because across period the atomic size is the same. When you lose the electrons, but the nuclear charge increases by right, the size of ion should decrease from sodium to magnesium to aluminum. At least for the first 3, it should go downward. Yeah, so it's not. I think it should be the other way around. It's go down and go up. Okay, size of atom. Size of atom, atom itself, these are all in the same period, all 3 shells. The nuclear charge increases across the group, So by right, having said number of shells and nuclear charge increase, it should go straight line down. Yeah, it shouldn't go up and down. Okay. Let's look at melting point. Melting point increases from sodium to magnesium, yes, aluminum. Silicon is highest possible, and then drop down to phosphorus. Yeah, so most likely it's this trend. This is only part that we may not really understand. Yeah, it depends on the molecular size of phosphorus and sulfur. If you know the details, phosphorus is P4, sulfur is S8. That's probably the reason why sulfur is slightly higher in terms of the larger molecular size. The molecule is made up of 8 atoms of sulfur. This molecule is made up of 4 atoms of phosphorus. So it's like that, slightly different. And this is 2. Okay, and argon is a lowest because it's a single monoatomic uh, particle. So therefore the size is the smallest, attractive force is the weakest. So answer is A. So it's good to know the trend. All right. Now, silicon down here, the melting point is the highest. Yeah, because of the strong covalent bond in the silicon itself. Strong covalent bond. They share electrons. Okay. Right. Okay, by the way, how do you know that sodium, magnesium, aluminum, the melting point increases? Now remember, metals, they lose their outer electrons to form positive ion in a sea of delocalized electron. So in the sea of delocalized electron, every sodium contribute 1 electron, magnesium contribute 2, and aluminum contribute 3. So two things happen. First, the metal ion has higher charge. So the sodium plus attract the electron C is 1 single plus charge attracting the Cl electron. Magnesium is 2 plus attracting the Cl electron, and aluminum 3 plus attracting. So the higher the charge of the ion, the stronger attraction between the ion and the C of electron. At the same time, the number of electron contributed by each atom is more. Sodium contribute 1. So there's 100 sodium atom, there will be 100 electrons around. If it's 100 magnesium, there will be 200 electrons around. So there are more electrons available to hold on to the positively charged magnesium. So the first reason is the magnesium charge is higher, and then there are more electrons. Okay, so there's stronger attractive force. Likewise for aluminum. So therefore it goes up higher as the nuclear charge increase and the amount of delocalized electron increases. Yeah, stronger attractive force in the metallic bonding. Okay, next one. Let's see. Number 15. 15. Let me see. Okay, this one is group 2 element similar reactivity. Similar reactivity trends. Not talking about same reaction, but reactivity increases down the group. That's what they mean. Z is found to be in group 2. Okay. How do you know Z can be between calcium and strontium? Okay, calcium and strontium. Calcium is above strontium. Strontium is below. So strontium below, strontium is more reactive than calcium. And Z must be more reactive than calcium. So basically, strontium displays Z, Z displays calcium. Okay? Strontium displays Z, Z. Okay, answer is C. There's no other choice already. Strontium displays Z to form the Z atom, and Z displays calcium. Because we know strontium is lower, calcium is higher. Remember magnesium, calcium. I don't even know the sequence below. I know strontium is at the bottom. Yeah, so Z is somewhere here. Okay, so that's how it goes about. Z displays calcium, strontium displays Z. That's all. It is a good question also. All right. Let's move to the next one. Oh, this needs calculation. Okay, 23.8 gram of potassium bromide and unknown mass of iodide is dissolved in this. Chlorine is bubble in the solution found that okay, the mass of oh gosh, this is interesting. Okay, I have two displacement reactions inside here. Okay, let me write the equation. First of all, chlorine will displace bromide. Hey, I must write the full equation, that's why. KBr to give you 2KCl plus Br2. And then I also have Cl2 plus 2Ki 2KCl plus I2. So I know bromide is this. I need the periodic table. I need calculator. Let's find the MR potassium bromide. Potassium bromide is KBr. Br is 80. 39 plus 80 is 119. So this is 119 MR. Ki will be Ki will be 127 plus 39. Ki is 166. Ki is 166. Okay, let's see. The 23.8 gram of potassium bromide, so it's 23.8 divide 119 equal to 0.2, a nice number. So you're given 0.2 mole of this. So how much chlorine do you need to react with 0.2 mole of potassium bromide? Obviously, this is 2, this must be 1, right? So it's 0.1 to 0.2. I need 0.1 mole. So 0.1 mole, 0.1 mole will be the volume. Volume will be 24 times 0.1 equal to 2.4 dm cube. So out of this 5.4, 2.4 is used to react with potassium bromide. Okay, so I must minus away 5.4 minus 2.4, left 3. So in other words, I got 3 dm cube here. Okay, 3 dm cube. 3 dm cube, let me find the mole. 3 dm cube divided by 3 divided 24. And that's equal to 0.125 mole. 0.125 mole, I will react with times 2. 0.25 mole of this one. 0.25 mole of this. So what is 0.25 mole of this? I multiply by 166. Okay, so I take this, multiply by this, times 166. And I will end up with having 41.5 gram of Ki. Answer is C. All right. So this question is a bit complex because chlorine reacts with both potassium bromide and potassium iodide. So given the mass of potassium bromide, I want to find out how much of my chlorine reacted with my potassium bromide. First, find the mole of potassium bromide, which is 0.2. Chlorine needed is 0.1. Volume needed is 2.4 dm cube. So out of 5.4, 2.4 is reacted with bromide. So obviously, 5.4 minus 2.4, 3 dm cube reacted with potassium iodide. So now let's calculate the mole again. 3 dm cube is 0.125. Equation 1 to 2, 0.125 is 2.25. So 0.25 multiplied with MR, that would be exactly the mass of the potassium iodide, okay, that reacts with the chlorine. And this is a very important question. You make sure you know how to do it. Is it okay? Okay, I think this one I would just send it. Okay. Is there any question to ask so far? No, let's move on then. Okay. No already. This is the last question. This is interesting. All right. I'll stop it here.